Hello and welcome back. Today we're going to change our mesh API so that we can go from something like this to something like this. Where if you look at the differences here, we're allowed now to interleave attributes within a single VBO, right? So here I'm defining a VBO with two different attributes, position and a color. I'm also, if you notice, have the ability to define a vertex buffer for a specific type. So really what we're getting at is arbitrary uploads, right? The actual backend code in Hippo doesn't know what data type you're uploading. We're defining it here as the users of the engine. And we're saying we have a vertex buffer of floats. Here's all the floats I care about. And then we have a vertex buffer of shorts, and this will be our texture coordinates. And you can see down here, the only change we have to do to support this is to update our vertex shader to support the new color that I added in the middle there. And if we run this real quick, you'll just see that we now have these additional colors that I've happened to add here in the client app. We now see those colors reflected in here. And again, the only change I had to do now that I have this new API is to add the data and then refer to it in the shader. So now, even though we're only adding color compared to where we ended last video, I think this will be a really interesting video if you're interested in more of the backend refactoring piece to really expose this in a really nice API in a way that we can be a lot more dynamic and as a user have a lot more agency around the data that we're uploading to the GPU and how we're exposing that data. So let's go over a walkthrough of what the old API was doing so that we can sort of break it down and see how we can rebuild it with something that's a little more dynamic. But first, like always, please consider subscribing, giving me a big thumbs up. It really does help the channel. And with that, let's go ahead and get started. So to start, let's look at what we currently have. In main.cpp, you can see our editor class has a mesh. And internally, in the initialize method, we're defining all the data for that mesh and then passing it along to the meshes constructor. Now the way we've got this set up is we define this float array of vertices, and these are vertices, and they have to be vertices because the mesh constructor expects it to be vertices at the, sort of in the first spot here. Then we have an elements array and a texture coordinates array that we added last video. Now the texture coordinates again have to be its own array because again the constructor expects that to be in its own array. So what this doesn't support is interleaving of attributes, right? And we talked about this a little bit in the rendering theory video, which if you haven't seen, I'll put a link to it below, and you'll probably see a little box in the corner right now if you want to go watch that. But ultimately, the API that we currently support it's not that great. I mean, we expect the caller to provide its own arrays for vertices, elements, and text coords, and then pass them in with these additional values. For example, this is the vertex array and then the number of vertices, right? 4 vertices. If I was to add 2 more vertices, I'd have to remember to come down here and update this to a 6. Similarly, each vertex has 3 dimensions, but if I was to remove the last dimension, which currently we don't really use, it's just 0 all the time, and I was to make this a 2-dimensional vertex, then again I'd have to come down here and remember to lower the 3 since the third parameter defines the dimensions of the vertex array. So once the user has set all this stuff up, they can finally construct this mesh. And if we look at sort of the definition here, again, it's a very rigid implementation, right? Like last video, we wanted to add texture coordinates and we required an entirely new constructor to support that. And that's because of 2 things. One, the constructor is what actually makes all the OpenGL calls and uploads the data to the GPU. It all happens when you construct the mesh. And 2, we don't have a way of arbitrarily uploading any data right now. Right now, it's very bespoke. I have a vertex array. It is a float array. I have a vertex count and I have the number of dimensions. That's the easiest example. Adding elements was an additional thing, right? And then adding texture coordinates was again an additional thing. And if we just switch over to the CPP, this is very explicit. And you can see that in the simplest case here, we're actually generating a buffer that we already know its positions, right? We already know this. And then we're binding it and then we're copying the data into it. And again, we know they're floats because we're forcing you to give us floats, right? We know there's going to be a certain number of dimensions and the number of vertices. And we know that there's no interleaving because we don't support it, because we explicitly in GLVertex strip pointer pass in a 0, 0, right? No stride, no offset. So there's absolutely no way that we could interleave any information per vertex, right? This is all very bespoke, it's very rigid. Again, moving down, the elements buffer I'll skip over because it's kind of a special case because it's a different type of buffer. But again, here, when we added this constructor to support texture coordinates, we're again having to very explicitly say, here's a new buffer of floats. This time it's very explicitly 2, right? If I, for whatever reason, I wanted to have, texture coordinates and colors, for example, I don't support that yet, right? I would need a new constructor, again, to copy a lot of this code, and it just gets really tedious. And really, I keep using the word rigid, but that's the best way I can describe it, right? The user of the engine is now forced to use what we give it, and it has no agency over what to upload to the GPU. And if I wanted to add support for something like colors per vertex, I would need to update the mesh class, have a new constructor, which ultimately means I have a new version of the library to ship to users that are using this library. All this to say that it's a very rigid system, and I'm not a fan of it. So in this video, we're actually going to get rid of the mesh class altogether. I don't want it, I don't like it, it's not good. What is good is a way of actually defining an API that allows us to arbitrarily upload data. And when I say arbitrary, I mean that at the point in which we copy the data to the GPU, we don't need to know that they're floats. Like we don't need to hard code this stuff in here. All we need is a pointer to the start of a memory address and then a size that tells us how much the data I want to copy. And it should just do it. And it's up to the user of the engine to ensure that when they set up a vertex array, it maps correctly to what the shader expects on the other end. So let's switch over real quick to Milton so I can break down these concrete steps, which will help us better put together this arbitrary system. So the first step is defining the data. And if you saw this in main.cpp, where we explicitly create a vector of floats that I've decided to define the vertex positions. Now what you're looking at here is 3 vertices, each with an x, a y, and a z position. Right, so these 3 vertices, when rendered, should be a triangle of some sort. So this row is vertex 1, this row is vertex 2, and this row is vertex 3. And all of this belongs to a single VBO. Now, what we did last video was we added texture coordinates, right? And so that was defined as a U and a V for each vertex. And again, vertex 1, vertex 2, vertex 3. And all of this was its own VBO, right? So this is VBO 1, this is VBO 2. What I want this new API to support is, instead of breaking up the data per sort of conceptual definition, for example, in this case, conceptually these x, y, and z's are positions, and conceptually these UVs are texture coordinates, right? I want to sort of flip that on its head, and instead of separating them by what they conceptually mean, I want the user of the API to be thinking about each vertex, not each contextual piece of data, and then having to write it out separately for each vertex. That can be sort of difficult to maintain. So what I mean by that is that if we were to have a new API, VBO1 would just contain data per vertex. So it would have, for vertex 1, it would have x, y, z, and then a u and a v, right? And then vertex 2 would have x, y, z, u, v. And vertex 3 would have x, y, z, u, v. And this again is called interleaving, right? I'm saying that there's position data for vertex 1, and then texture coordinate data for vertex 1, and then position data for vertex 2, and then texture coordinate data for vertex 2, etc. And so when we're talking about defining data, I want the API to be very vertex focused, right? I want to be able to push a vertex into a VBO instead of having to sort of conceptually break it up into these 2 separate arrays. Now, one thing we haven't talked about yet is the types, right? And before, again, they had to be floats. I don't want to force types here, right? Like I don't want to force anything on the user. I want them to tell me what types they're using so that I know how much data to upload to the GPU. So my thinking is that each VBO would have a data type associated to it. So I could have this VBO would be, let's say, floats. And so I know that every data I'm pushing into this VBO is a float. If I wanted to track ints, that would have to be its own VBO. So VBO2 could be ints, and then it would track its own data. Now I could take it one step further and split up what this data type is and this data type. But I think that would complicate the API a little more, because really what I ultimately want to be able to do is say, here's my vertex, right? So really I want something like this, VBO.push vertex. I should be able to pass it an initializer list of a vector, in this case a vector, and let's say my VBO is a VBO defined for floats. So now I should be able to push an array of floats, and again I'll do my x, y, z, u, v, and then I should be able to call VBO.pushVertex and the next vertex, and so on and so forth. And then at the end, or even at the beginning, it doesn't really matter. I just also need the contextual piece about where this is split up. right? Because this is going to determine our stride and offset, right? So then at the end, I could do something like vbo.setLayout, which is the layout of my data. And in this case, it would be, because they're all floats, I know that's all I have to tell it. It's just a matter of how many floats per attribute, right? And in this case, it would be 3, 2. And that's it. So yes, it does take a little more code for the user because they have to define this layout and they have to sort of, if they change the layout up here, they have to change it down here. But I'm willing to trade that for the flexibility and versatility of this new system, where I should really be able to just interleave attributes like this within each vertex. And again, it's the key is that arbitrary upload, right? Here, I'm, as the user of the engine, defining that we're using floats. I'm not forcing it on anybody. I could change this to ints, and that would work just as well. Now, similar to my VBO objects, I want a VAO object that I could call maybe push buffer on, and I would pass in my VBO one here. So again, I can define my data however I want to, and then I define my VAOs. This also allows me to define VBOs that are used by multiple VAOs. Now, we did talk about element buffers, and that still needs to be a thing. Now, element buffers are unique to a VAO, so I want the VAO to also be able to have something like set elements. And because element buffer is always a UN32_T array, I could just pass in an initializer list of integers, right? Like, I think for the rect it was like 0, 3, 1, and then 1, 3, 2. It should be this simple, right? It's converting this sort of stuff into a class-based structure with an API that makes sense. And now finally, once we have the VAO and we know the VBOs that are attached to the VAO, that's when we can upload the data and set up the attributes, right? If we go back to our code for a second, we can only call this enable vertex attrib array and GL vertex attrib pointer when we have the data we're talking about bound, right? This is saying the currently bound GL array buffer will be my attribute 0. And then here's the information about it, right? So this step, because we're arbitrarily defining these buffers and this data, I can't quite do this immediately, right? And in the case of this mesh class, we were able to get all of this done in the constructor because we were so rigid that we could actually get away with that. And it was very simple from that perspective. But because I'm going with this sort of separated VAO VBO structure where my VBOs are one thing, my VAOs are another, and then I sort of link them here with this API, I don't really have a good place to put that last bit of code there that enables the attributes and defines what that attrib pointer looks like. So I'm going to have an additional call, maybe VAO.upload, that does that for me. So this is basically me saying, hey, I'm done defining this VAO. You have all the buffers you care about. You have the elements. Go ahead and upload yourself to the GPU. So this sort of wraps up my explanation of the API and what I'm going for. So let's just jump into the code and start building this thing. So let's go ahead and create a new file. We'll call it Vertex. And this will sort of house all of our Vertex attributes, Vertex buffers, that sort of thing. We'll do the same for the CPP. Now, I talked a lot about arbitrary uploads. This really means that I don't have a float star to upload. I don't have an int star, right? I have a void star. It means I don't know the type. All I know is a memory address and a size. So I'm going to start with a class called RawVertexBuffer. This is just going to house everything Vertex, like VBO related, except for exactly knowing what type our data is. Now I'm making this virtual right up front because I know I'm going to subclass this class. Let's make a protected section. And this will really be a lot of what the mesh already had. So UN32_T for the VBO. Another one for maybe the vertex count, which we'll need to know. I also need to know the stride. And this is what's going to allow us to interleave those attributes. Now, as I mentioned earlier, we're going to need to know the layout of our data, right? How many floats or int or whatever they are, how many of those are one attribute and how many of those are a different attribute, right? What is the split when I'm interleaving these things? So we'll have we'll just track that as a vector of un32_t's bottom layout. I'll include vector, which will include cstdins for these. Perfect. And now again, that void star. And working with void stars can be a little scary, but it's not too bad. As long as you have an accompanying size so that you know how much data you're dealing with. So un32_tm size, that should be good for now. Now let's go up and write some getters here. It's actually on VBO. I don't know if anybody else external to this class needs to know the stride, but let's just return it in case we want it. And that should be it for getters, but we'll need to set the layout. Layout, yep. And then again, I talked about that upload. That's going to be important. So upload, and if we just look back at the mesh real quick, our upload, yeah, it needs to know if it's static or dynamic. But this is just to help OpenGL optimize your data by putting it in a place in GPU where it's easier to write to or easier to read from, that sort of thing. So maybe I'll just pass that in as a bool here. Default to false. And then, as always, we'll have our bind and our unbind. I think that's enough. So let's just right click on the class. Actually, we'll switch over. There we go. Now we can do this. And so we'll know we're making OpenGL calls here. So let's include glad. We'll probably want our helpers as well. Perfect. So yeah, when we instantiate a RawVertexBuffer, we'll call it glgenBuffers. We'll call hypocheckGLError after, and then we'll call the same thing here, but it'll be delete buffers instead. Good. And now for set layout, really we just want to copy that layout over. And switching back here for a second, if we look at this, maybe I'll just sort of redraw it over here. When we're saying we have a layout of 3, 2, we're saying we have an X, a Y, a Z, and then a U and a V, right, for each vertex. Now this layout, the reason we need it is because we need to be able to know what that stride is. And as a recap, what stride means is that, let's say we have our vertex 1 and our vertex 2 here, right? X, Y, Z, U, V. What that means is that if I'm defining these as attribute 1 and these as attribute 2, which means these will end up being a vec3 in the shader, and these will be a vec, and A2 here will be a vec2 in the shader, right? In order for that to work, OpenGL needs to know the stride between all of the vec3s for each vertex and the stride between all of the vec2s. And really all that means is it needs to know how much data there is per vertex. Because it's going to go for attribute 1, vertex 1, it's going to say, okay, I start here, X, I have Y, I have Z. Now where's the next vertex's X, Y, and Z, right? So it needs to skip over a whole bunch of them. So what you give it is the stride from the first value in the attribute to the first value in the attribute for the next vertex. So in other words, it's the number of bytes between the first X and the second X, right? So it's got to be bytes because it's just an offset really when we're talking about the attributes. So attribute 1 will say, all right, I'm going to read my X, Y, and Z, and then it needs to know how to get to the next attribute 1 for vertex 2, so how to skip these. And really, the other way to think about it is it just needs to be the number of bytes per vertex, right? The number of bytes in each row. So we can get that with 3 plus 2 times the size of this type, which might be a float, for example. And that's one reason we need 3, 2. The second reason is that when we're actually calling glVertexAttrib_pointer, where we pass in this stride, we also need to enable a VertexAttrib_array for the particular attribute count, right? So this is how we know it's attribute 1. And then our offset in this case is 0 because attribute 1 is the first thing in this row. And then for attribute 2, our offset is actually going to be 3, the number of bytes to get to attribute 2, right? So the offset from the start to get to the start of attribute 2. And obviously if we had a third set of attributes, this would be attribute 3, which would have its own offset, which again would be an offset from the beginning all the way through to get to attribute 3. So that's what we define it as, a vector of ints like that. Now again, back to this, we copy our layout, and then we're going to set our stride to 0 to start, and then for everything in our layouts, we'll just say mstride plus equals count. And now you might notice this isn't currently the number of bytes in the row, right? This is currently the number of floats in the row, right? I haven't multiplied it by the size of a float yet, but I can't do that here because this is the raw vertex buffer, right? I don't know what the size of my internal data structure is because I keep saying floats, but they could be UN32s, they could be doubles, they could be something completely different. They could be shorts, right? They could be bytes, it could be anything. So what I'm going to do is keep stride as the number of values, let's call them values, the number of values per vertex row. And then when we actually upload the data, we'll multiply it by the size of the type, which won't be able to happen in this class. We'll do it in a subclass in a second. But at this point, now we have what we need in order to actually upload. Because again, it's arbitrary. I don't care what's in mdata. I don't care what msize is. I just care that it's there so that I can upload it to OpenGL. So here's where we're going to actually do the upload. So GL bind buffer. Let's copy this. And then we'll bind 0 when we're done. And we'll just call it GL buffer data. And now it's the size, so we'll pass in msize, which we haven't set yet. Again, we don't know what msize is because we are the raw vertex buffer. But we're hoping somebody sets this for us. And the void start data, we don't have to cast anything over. We're literally passing them data through. And then the usage, if it's dynamic, it'll be dynamic, otherwise static. So we can just do a dynamic GL dynamic draw. Otherwise, we'll use GL static draw. And again, let's take this. And there we go. That's it for the upload. We have done our arbitrary upload, which is great. And then for bind, yeah, we'll just call this here and this for the unbind. Okay, so that's pretty straightforward. Now let's switch back to our header, and now we'll get to the interesting part. It's how do we define a class that the user can determine the type of. And if you're not familiar with templates, I would suggest you read up on templates and play around with them, figure out how they work and what they are. I'll touch a little bit on what they are here now. I'm going to create a templated class, and the template, it will be a template type name T. And I'll call this class a VertexBuffer, right? And it's going to subclass RawVertexBuffer. Now, this doesn't care about the VBO or whatever, the parent class has all of that, and we have access to it because it's protected. But what this does have that the base class doesn't is the type of the data we're dealing with. So let's create a std vector of T. And so really what this is doing is that when I create a vertex buffer, I have to tell it a type. I have to pass in a type with a special syntax. And that will be referred to as T within this class definition. And then when it comes to time to compile the code, the compiler actually comes through and figures out every time that you call VertexBuffer with a float, for example, it actually will generate a VertexBuffer float class very specifically, and it'll replace every T with a float. And really this is a shorthand for us to be able to write something that's sort of dynamic, but that is still going to be compiled at compile time, and it's not going to do any additional runtime stuff for us. So here we'll have a vector of whatever data type I've decided. We'll call it mdata vec, I guess, because we have mdata above. So this is mdata vector. And I mentioned I wanted a push vertex style thing, right? So we'll have a void push vertex. And now we can just take in a constant vector of T reference, and we'll call it vert. And so we have mVertex count that we want to set here. So when I push a vertex, it means I have an additional vertex, so mVertex count plus plus. And then we're just going to append to our data vector down here. So we can just say mdatavec.insert, and we'll insert at the end, so mdatavec.end, and we're just going to insert vert.begin to vert.end. And this is how you concatenate sort of std vectors together. And now the upload up here, this is the arbitrary upload that again expects msize, mdata to be set properly, right? So why don't we actually make this virtual and override it here. So void upload, and we'll take in that bool again for dynamic. So because mstride from the parent class is currently the number of values, we just need to multiply it by size of t here. And this is the beauty of template classes. You can just do this. It will just work. Once you compile this, this will become size of float or size of int or size of byte or char in C++, whatever it is. Now again, RawVertexBuffer's upload method does expect msize and mdata to be set properly. So let's start with msize, which is easy. It'll just be, again, the size of t, whatever data type we're dealing with, and then times the number of values of that data type that we have in our mdatavec. So mdatavec.size. And I should probably cast this to a un32_t here. And now mdata, which again is just a pointer to the start of our data. So because we're using std vector does guarantee that all the data within it is contiguous in memory. So we can just point mdata to a reference to mdatavec at 0. And so mdatavec at 0 will give you the first element of the vector, and then a reference to that first element gives you the memory address where that first element is stored. And because std vector is contiguous, this will be the correct starting point for our data here. And we can do this because once you upload the data to the GPU, OpenGL will just refer to that memory that's already in the GPU. It won't come back and look at mdata on the CPU. So it means we can do this safely. mdatavec can change after we do this, and it won't affect what's actually uploaded to the GPU. Now I do want to assert here that msize is greater than 0, because I don't want to try and call mdatavec at 0 if there is nothing in mdatavec, because I'll try to access the first element in an otherwise empty vector, and that will crash. So I'll just do an assert just so that we can catch it. We really shouldn't ever be trying to upload a VBO that has no data associated with it. So this assert will help us track down the situations where we are trying to do that. Okay, and now that we've set everything properly, we can safely call the parent's upload method. So RawVertexBuffer : upload, and we'll pass in the dynamic here. Now in order to properly test this, even though we're not rendering anything yet, let's just add a print here. So hippotrace So now with this trace, we can actually test this. Even though we won't see anything on the screen, we'll see that we're properly uploading what we expect in terms of size and stride. So let's switch back and do that now. First, I guess we'll have to include Vertex. And now down here, I'll just say graphics. So I have a RawVertexBuffer and VertexBuffer. So I want a VertexBuffer. And now when I'm using templated classes, I have to tell it the data type, right? What that T is. In this case, I'll do an open hairpin bracket and pass in a float. So I'm saying this is a VertexBuffer of floats. I'll call it VB. Now this should create something for me. I can now say VB.pushVertex. And let's say I want to push this data up here, right? So 0.5f, 0.5f, 0.f. That's how I would do the first vertex, and then I would just do this 4 times. So now this one's negative. Now these two are negative. And now just this left one's negative. And now I should be able to call set layout and just tell it that I'm dealing with 3 floats. And yeah, this will have to be wrapped in squiggly brackets because it is a vector. So I'm dealing with just 3 floats. It's going to be a single attribute. And now I have everything I need to be able to call upload. And what I'm expecting here is to have a print. The size is going to be sort of all of these as floats. So this is 3 times 4, because 3 floats per vertex, and I have 4 vertices. And that's 12 bytes. And then they're all floats. So then I have to multiply that by 4, which is 48 bytes. So the size should be 48 bytes, and the stride, it's only 3 floats. So the stride should be 3 times 4, which is 12 bytes. Let's go ahead and run it and see what we see. And here we are. So our VertexBuffer upload was successful, and it uploaded 48 bytes in total with the stride as 12 bytes. Perfect. So now what we should be able to do is add the texture coordinates to the end of this, right? Now it'll have 1.f, 1.f, and then 1, 0, 0, 0, and 0, 1. And now my layout is 3, 2. So now it's 5 floats per vertex times 4 vertices. That's 20 bytes times 4 is 80 bytes total. And again, 4 is because it's the size of float. So I'm expecting 40 bytes, and now the stride should be 3 plus 2, which is 5 floats per vertex, and then times 4 for the size of float, which is again 20 bytes. And sure enough, we get 80 bytes total, 20 bytes for stride. Okay, so that's perfect because that means that our stride value is correct, and we can use that to ensure that the attributes are interleaved when we come to writing the VAO. So let's do that next. Okay, switching over to vertex.h, we're going to add our VertexArray class, but before we do that, I'm just noticing that we haven't marked the upload method as override yet. We're going to want to do that since some compilers do care about that piece. Now let's come down here and create our VertexArray class, which is essentially going to replace our mesh class. And if we remember, just looking at our RenderCommands.cpp, when we render a mesh, we need to know the element count or the vertex count. So we should probably track both of those within our VAOs, just like we do with our mesh, right? So I'll have a UN32_T vertex count and element count. And then additionally, we'll have a UN32_T for the VAO and then EBO. Again, the EBO is separate from the VBOs, right? It's a unique buffer. But now is where it gets interesting because we can define an attribute count, which we couldn't really have done before, at least not dynamically. So now we know how many attributes we have because of that layout, right? 3, 2 means we have 2 attributes. And now again, because we have an arbitrary number of VBOs that we can push, just looking back to that API that we defined earlier, we're just going to have here a std vector of RawVertexBuffer pointers. Now this is key here. It has to be a RawVertexBuffer pointer. RawVertexBuffer is the parent class, and by using a pointer, we're allowing ourselves to use polymorphism to be able to call a RawVertexBuffer method, for example, upload, and have it actually do work on the internal vertex buffer itself. That could be a float, could be an int, whatever it is, to ensure that we call this upload instead. So it's going to be a RawVertexBuffer pointer, and these are going to be called our VBOs. And if you remember from our mesh class, we had very explicitly a position VBO, a text cohorts VBO, that's gone, right? It's not explicit anymore. It's now dynamic and user defined. So with all that set, let's just write our methods here. So VertexArray, and then we do some getters. And then I talked about that push buffer method. So we'll go void push buffer. And again, it'll be a RawVertexBuffer pointer VBO, which we'll just add to our VBOs below. And then we do need very explicit set elements here, right? So void set elements. And this will just take a std vector of UN32_Ts elements. Now the actual upload method that we're exposing is the upload on the vertex array itself, right? So for this we'll have a void upload, and then a bind and unbind. Great, let's get these all created. So let's just start with an initializer list here. So VAO will start at 0, EBO 0. Okay, and then we'll glgen this time vertex arrays. 1 VAO. Perfect. And now the structure is going to be a little different, right? So let's just write this out for our delete. And before we delete ourselves, we'll want to iterate over our VBOs. And gl delete buffers, delete 1, and this actually takes a pointer to the buffer. So let's just create a UN32_T up here, ID, and we'll just say ID equals VBO-arrow get ID, and then we'll just pass in a reference to ID here. Oops, ID. And because these are raw pointers, somebody needs to delete them. So what I'm thinking is the user will call new on the VBOs, call push buffer on the VAO, and the VAO will now assume ownership of that pointer. So it will call here delete VBO. Then we delete the VAO, and then we can just say mvbos.clear. Good. Now the push buffer. So we just do mvbos.pushback VBO, right? Now this is going to get a little interesting because if we're thinking about here, where we're doing something like this, and then we'd have something like VAO.pushBuffer. That's what I called it, I think, VB. So in this case, I would push a buffer that has, in this case, 4 vertices, right? But if I had another buffer, for whatever reason, I had an int buffer, VB2, oh man, we have to change all of these. Let's just make it a float for now. But the point is that if I had something like this, where my first buffer has 4 vertices and my second buffer only has 3, that's going to get weird because our VAO would expect every VBO to have enough data for every vertex that it knows of, right? So I should be able to catch this edge case here and basically just say that the first VBO that we push to the VAO is going to define the number of vertices that I'm expecting for every subsequent buffer, if that makes sense. So in this case, I would push VB first. It has 4 vertices, so that's what I know I'm going to need to expect from everybody else. Then I try to push VB2. I see it only has 3 vertices. That's where I can easily sort of throw an error or an assert, and we should be good. So let's go ahead and add some logic to track that. So if we have something in VBOs, then I can just assert on mVBOs at 0, so the first one I pushed, get vertex count equals the one I'm passing in, so VBO-arrow get vertex count. Otherwise, I'm attempting to push a vertex buffer with a different vertex count, right? So it's a pretty easy check. Now I guess the other check I can do here is just ensuring that the VBO I'm getting passed in has a layout defined, right? Because we want the API to be very explicit in saying there are 3 floats and then 2 floats, even if it's just one attribute, right? Like I want to see that number 3 because that's what as someone using this engine, I want to see here's my 3 in C++ and then here's my vec3 in the shader, right? I want to see that correlation. So I'll just also maybe assert here on VBO-arrow get layout -arrow size or dot size and assert that it's greater than 0. Otherwise, I usually like to put these here just to know where they came from. And I can just say VertexBuffer has no layout defined. Cool, and then I'll just do this. Wrap this in a check. So only if we have a valid layout do we push back. And then maybe here I can just say my mVertex count. Just set it to a uint32_t of mVBOs at 0. -arrow get vertex count. And yeah, this should be a fine place. Like I might push 5 buffers and this will just get reset to the first number of vertex counts 5 times. But that's fine as long as it's the same number. So that should be it for push buffer. So this is for arbitrary buffers, and now set elements, we'll just write this one down real quick. So element count is elements.size, and I have to cast this to uint32. And then if we remember how to do this from the mesh, it's quite simple, right? So gl bind vertex array, we'll bind ourselves. And then where's that hippo? Check gl error. And then gl gen buffers 1 stored in an EBO. Then we bind it. GL element array buffer EBO. Then we'll copy the data over, so GL buffer data, GL element array buffer, and this time it's elements.size times size of UN32 underscore t. I wonder what that will be. And then pass in just the data, so reference to elements at 0. And elements won't change. I'm just going to make that assumption here. So GL static draw. And that should be it. And so obviously this is much simpler when you're defining with a very specific type, and it's easy to define the size of that and all that. But yeah, and then we'll just unbind the vertex array. And just remember, you don't unbind the EBO, right? The EBO has to stay bound within the vertex array itself. So we don't unbind the EBO, we just unbind the VAO here. But now we can get to the fun part, the upload. So here's where we're going to bind the VBOs to the VAO and use that stride and offset to map these attributes to these potentially interleaved vertex buffers. So first let's bind. And for VBO and MVBOs. Now, before we do anything, we need to ensure that the VBOs have been uploaded, right? So back over in vertex.h, we really just want to ensure that this has been called, right? Like that this upload actually happened and that something's on the GPU. So let's go ahead and add just a bool here at misuploaded. We'll start it as false, and we'll just expose it here. Bool is uploaded. And then we'll just set it within the upload back over on the CPP side. And then only when the parent class upload is called do we say it. M is uploaded equals true. So because right now our main.cpp is calling upload on these, and it's going to do that for each one of them. And this is what's going to allow us to actually define something like true if it's dynamic, right? Obviously the VAO doesn't know that because it's on a per vertex buffer, not on the per vertex array. So I'll do that, but if I don't call them, I'm just going to assume they're all static, right? I'm just going to call upload from the vertex array with no parameter being passed in. So here I can just say if VBO-arrow is uploaded, and here in this case if it's not uploaded yet, so if the user didn't call it or was explicit about it, I'll just call it here, VBO-arrow upload, and I won't pass in dynamic, which means it'll be false. False. Yeah. I'll be explicit here and say if you didn't do it, I'm doing it for you, and it's going to be static. Okay, and now that it's for sure uploaded, we can say VBO-arrow bind. And now I can iterate over that layout, right? So for UN32 underscore T count in VBO-arrow get layout. And here's where we're going to actually bind the two things, right? So here we've bound the VBO. And now that it's bound, it means that when I call GL vertex attrib pointer, it's going to refer to this currently bound VBO. So the first thing we do is enable it. So GL enable vertex attrib array. And then we have to enable the attribute. Now in this case, it's the index, or what I usually refer to as attribute ID, which we don't have, and we need, it sort of goes up with this array, right? So let's just have a UN32 underscore T attribute count equals 0, and we'll use attribute count here. And then we'll, again, just do this. Basically, at the end of this for loop, we're going to say attribute count plus plus, right? But now that we've enabled it, we can make the most interesting call of today, which will be GL vertex attrib pointer. And so let's see, the index again will be attribute count, which we just enabled. Size, I don't like the name of that. It's not the size, it's the number of components, right? And it actually only supports 1, 2, 3, or 4. It's one of those 4 values. But in this case, the size will just be count, because count is the part of our layout. So count. Now the type. Now, I keep saying we have arbitrary types, but I actually don't yet have a way to pass the type in here properly, because this expects a GL enum type, so like GL underscore float. We don't have this sort of abstracted yet. So for now, I know the point of this video is to have arbitrary uploads, but for now, let's just do GL floats just to get this part working. And then we'll come back and clean that up so that we can support non-floats, okay? For normalize, we'll just say false for everything. And the stride, here's where the stride comes in, so we'll say VBO-arrow get stride. Now for the offset, it's interesting because as I iterate over the layout, that's how I have to keep track of my offset, right? Because if we switch over to Milton real quick, in this example that I was giving before, here's my layout down here, right? In this case, it's 3, 2, 3. So when I'm dealing with the first count in layout, in this case, it happens to be 3, my offset's 0, right? Because we're starting at the beginning of the vertex. But when I loop over to the next count, I now have an offset of 3 floats, right? So my offset needs to be 3 times 4 here. So that it knows how many bytes into the vertex to get to attribute 2. So let's come up here real quick and just keep track of an offset. UN32_T offset equals 0. And the first time it'll be just offset. And now this is a void star, a const void star. So I have to cast this to a void star and then int pointer underscore t, because pointer sizes might be different based on your system. So you do this, and so that'll be our offset, and then we'll increment, let's just, before I forget, call this guy, and then we'll increment attribute count, and then we'll increment the offset, so offset plus equals, and now it'll be the count, which is the number of components, so in this case floats, so count, and then times the size of, again, I need to know that type. In this case, it'll just be the type of the vertex buffer, so maybe I can have like a helper method to give me that, right? Give me the size of the type. If we switch over to vertex.h real quick, I could just have virtual get type size, I guess. This will be const, but we'll make it equals 0 here, because this again doesn't know the size, right? And sorry, it'll return a UN32_T. And this will actually help me do 2 things. One, it'll allow me to sort of override it down here, but also it'll allow me to make this an abstract class so that nobody can create an instance of a RawVertexBuffer, which is good. So get type size will be just overridden in the child class down here, which will be very easy. UN32_T gets type size will be constant. It will simply return size of t, which we only know at this level, right? And this will have to be an override. And so now back over here, I can say, instead of size of anything, I'll just say VBO -arrow get type size. Okay, and that should do it, because then we get to the next count in the VBO. It'll be a new attribute count here. Still floats, again, we'll fix this, but it will be the same stride and then a new offset because we've updated the offset here. Perfect. So now at the end of this for loop, we can call VBO -arrow unbind. And then we unbind ourselves, and then we're set. Now, I don't want anybody trying to render with a VAO that hasn't been uploaded, so similar to the VBO, we'll have the VAO have its own bool here. We'll call it m_is_valid. Inline bool is valid. Const return m_is_valid. And in the constructor up here, we'll just set it to false to start. And now I'm calling bind and unbind, but I'm not actually doing anything. So bind VertexArray and VAO, that here. And maybe I'll replace this with those. I'd like to be explicit in line here. And unbind will be here. Unbind. So that's actually all there is to it. Let's try and get this working, and then we'll come back and clean up this GL float as sort of the last thing today. So if we go back to our render commands, remember we have these render mesh commands, right? And render mesh textured. We basically need the exact same thing, but for VAOs. And actually, I'm going to replace render mesh. I don't want this to exist anymore. So we'll say render vertex array. Update this, and we'll have to, instead of class mesh, I'll say class vertex array. We point it to a vertex array. And vertex array. Okay, and we'll do the same for the textured one. Okay, switching over here, I'll be render vertex array. Instead of mesh, you're pulling in vertex. Just call it VA here. Perfect. And then we'll do the same here. Actually, this one was outdated as well. Render VertexArray textured. Data, perfect. So now we should be able to render a vertex array. And all it's, you can see the API doesn't change, right? We're still binding it, getting elements or getting vertices, and then unbinding. That's all we're doing. So in main.cpp, we will just remove mesh. Let's just get rid of it. Vertex array will be vertex array. And now, thankfully, we can actually remove this old API now. And let's just first of all copy everything over. So we have a vertex buffer here. This will be a vertex buffer. Let's not call upload. This will be floats, and we'll use this for vertices and texture coordinates. So which I actually already set up here as 3, 2. So that's good. And then that's actually all I need. I don't need another vertex buffer. I just need the elements buffer, which is 031132. So now that we've defined this vertex buffer, I don't need to scope this. I'm just trying to get fancy. Now we can say mva equals just to make sure vertex array. But what we do is call mva-arrow, and then we'll call push buffer. We'll push vb. And now, yeah, this will have to be a pointer. So we'll say this is a pointer, and say equals new graphics vertex buffer float. And these will be dash arrows. And then mva-arrow, we'll just set elements. And here again, it's 031132. And then mva-arrow upload. So instead of doing everything up front and then calling constructor, which will upload everything for us, we sort of define the same data, but with a little bit more flexibility down here, and then we call upload instead. But that should do it. So let's remove this. We have these two. Do we need this second thing? No, we don't. That was just me showing stuff off. Okay, so we have this, and now down here, basically where we're drawing our mesh, we're now saying we're doing a render vertex array textured, and just passing in mva. Okay, so because these are floats, it's the only one I support right now. Let's run this, and hopefully we see no change whatsoever. And this is great. We don't see any change, but we're not rendering a mesh anymore. We're rendering a vertex array. And this is really exciting. This is great. But the key to all this is that we can upload arbitrary data, right? Right now, I don't support any vertex buffers with like ints, for example, right? So let's do that as a last step here, and then we'll use this to upload some additional data per vertex. Switching to vertex.cpp, this is the thing we need to change, right? So what I really want is for, just like I have this VBO-arrow get type size, I want something similar, like VBO-arrow get type, right? Now the type itself, it needs to be GL-enum, and if we look at what this was before, GL float, if I LG on it, you'll see it's something very specific to OpenGL, and this is just glad.h that does this for us, right? So these are the values that we pass into that call. So this is what I need to be able to abstract out away from glad.h and be able to expose it in the parent class. So let's go back, and again, this will be a GL-enum, so I'll just do a static cast, because I'm not going to track them as GL-enums on the engine side, but I'll cast this to a GL-enum. It'll just be an int. And let's just call it VBO-arrow get, maybe get GL type. We'll be explicit about what this is. And so this is the method we need to support. So just like get type size, in the parent class, we'll need another one. First, we'll track it down here as the type. So maybe here, un32_tm GL type equals 0. And now again, similar to like what we did with the buttons for SDL for a mouse or a keyboard, we don't want to include glad here because the like hippo editor doesn't know what glad is. So instead what we'll do is we'll just have a public set of abstractions to these types, right? So it'll be a static const un32_t GL type, and then I'll just name them byte. uint32.t. Yep. And really, we should only support the types that OpenGL supports for GL vertex attrib pointer. So we can refer to OpenGL's documentation to see exactly what is supported. And you can see here's the specification for GL vertex to trip pointer. And for type, it's very explicit. So the symbolic constants GL byte, unsigned byte, short, unsigned short, int, unsigned int are accepted. And then half float, float, double, fixed, and then these crazy ones at the end are also accepted. So I'll support basically everything up here, up to unsigned int, and then floats and doubles. I won't bother with half floats or anything else. So those are the types of support: 1, 2, 3, 4, 5, 6, 7, 8. So it's byte, unsigned byte, short, unsigned short, int, unsigned int, float, and double. And just to be quick here, I'll just write ubyte and then short, ushort, int, uint, float, double. And by making them static consts, we can define them here and then initialize them in the CPP, which is exactly what I want. Because here I can access glad.h. So here we'll say RawVertexBuffer : and we'll set these equals to the GL enums, right? So GL underscore byte, GL underscore unsigned byte, GL underscore short, Okay, perfect. So now that we have this abstraction, we can actually go ahead and set this for myself over here in the templated class. And really we can set them right here. But because this is a templated class, I'm saying I only support these types, right? So I need to ensure that T is only one of these types. For example, I can't pass in string. Like I can't have a vertex buffer of strings, right? That shouldn't be allowed. So we can actually use a little helper here in, I believe it's type traits. Yeah, type traits. So by using type traits, I should be able to come down here and basically add a static assert. So static underscore assert. And this is what a static assert is. It's an assert that will trigger when you're compiling your code. So it'll tell you that you've done something wrong. For example, I should never allow a vertex buffer assert string to be compiled, right? So that's what a static assert will help us do. And so here, I'm just going to say that my static assert is going to check for, using type traits, we can have std is same, and then I can check that t is the same as a char, for example. And again, char is how we represent bytes in C++. So is same, and this is a function call basically. So I'm asserting that t is a char, or t is an unsigned char, right? And we can just sort of refer to what they are. So this is for GL byte. This is for GL underscore unsigned byte. And so then we have short, short, int, float, and double, right? So short, unsigned short, int, unsigned int, and then float and double. There we go. And this doesn't need an or here. And so static assert, just like my hippo assert, right? It takes your condition, and then it takes something to print if that's not the case. So in this case, I'll just say this type is not supported. Okay. So, okay, great. Now I'm ensuring that I can't create a vertex buffer of such strings, but I'm still not setting our GL type up here, right? So I need this mgl type to be set to one of these values, which is ultimately what is going to be used in the vertex to trip pointer call. So in the constructor here, I can do something as well. Basically going to be the same checks, right? Let me just clean this up just a little bit. Just going to remove all of this, because really what I'm going to do is check for these and set the value depending on what it is. But I can do all of these at compile time as well, so I'm not actually going through an if statement or branching out at runtime. And you do this with an if const expr. And again, this is another one of those things that I won't really get into, but if you're interested, you can definitely read up more about it. So I'm going to say, and really this will be for everything, if const expr, and I'm saying this, right, so if any one of these is correct, then I'll just say mgl type equals raw vertex buffer gl type, and in this case byte. And by using const expr here, I'm basically ensuring that this will always be, this will be the deduced at compile time, and only one of these branches will actually be compiled into the final code. There. And so then again, this is byte, this will be u byte, this is short, and this will be u short, int, and this is uint, this is float, and this is double. That is it. We should now be properly defining our GL type and using it. So maybe what I'll do is I'll run it, but I also want to make sure that this is set properly. So I'll just put a breakpoint here. And what I'll do is in main.cpp, and actually I want them there for reference before I do that. So this will be VB, and we'll do it this way. So create a vertex array, and then I just like to scope this because then I can reuse the same name. But here I have a vertex buffer floats called VB. I'll push all this data into it, and I guess now that I have a copy, I can get rid of these. And so this will just be 3, and this will match this vec3 position here. So that 3 is this 3 here. And now I'll push that buffer, and then I'll come down here and create another one, this time of shorts, okay? Short. And here, we'll just get rid of these. And get rid of the pointfs to make them truly shorts. And this will just be 2. And again, this 2 maps to vec2 down here. And then we push that buffer. And now for fun, let's just try and say a graphics vertex buffer of std_string test. And now this shouldn't compile, this should trigger my static assert. But then we're setting the elements and uploading. So this actually should be a good test. I should be able to upload this and have no difference in what we're seeing, but it should actually take up less memory. And I think we were seeing 80 bytes and then the stride was 20 bytes. So we should actually see a lower number now. And yeah, we don't compile, so vertex.age error, this class is not, or this type is not supported. And this is happening here on main.cpp line 68. So there you go. That's a great way of ensuring that we don't try and create vertex buffers of types that aren't actually supported on the OpenGL side. So let's try this again. And this time, oh yeah, I put my breakpoint because I wanted to make sure GL type was right. So in this case, if I F11 into it, my GL type, oh, it's all inline, so I won't actually be able to see the value I'm trying to check here. And I actually won't see it going in either. So you know what, that's fine. Let's just F5 and see if it worked. And yeah, so you can see nothing's changed. And if we look at this though, yeah, so this is exactly what we're talking about. So if we go back to our main.cpp real quick, just for reference, the first buffer upload is 48 bytes total with a stride of 12. That's 4 times 3, because it's 4 bytes per float times 3 floats is 12. But then down here, it's only 16 bytes of an upload, because shorts are only 2 bytes per int, right? So I have 16 bytes total with 4 byte stride because it's 2 bytes per int, and I have 2 ints per vertex. So you can see that this already is good. Like, we're already technically saving memory here. And I mean, when we're rendering a single rect, it's negligible, but when we're rendering something that potentially could have a lot of vertices, this is where you'll really see the savings come up. So now that we've got all of this set up, I should be able to add some data to my vertex array very quickly without needing a new constructor, and I should be able to just see it work. So this is where I want to add colors, because that's a really easy way of seeing it. So I can add it here. I could create a new vertex buffer, but because I'm supporting interleaving here, I'll just add it to the end. So I'll say that the first vertex will have a color of white. second vertex, we'll give it, I think 101 is my magenta color. And then we'll go 1, or maybe 0, 1, 1. And then we'll go with a green 0, 1, 0. Okay, so now I've just added some data to the end of my vertices, and now I'm saying I have 2 different attributes, 3 floats each. So now one thing to be careful of here is that because of the way I'm iterating over each vertex, each VBO, and sort of dynamically creating the attributes from them, this will actually be index 0, the position, and then the color will actually be index 1, and now the texture coordinates have been pushed down to index 2. So I have to reflect that here, right? This is now position 2, and I have another vector 3 in position 1 for color. And now again, well, just like we did when we originally had these shaders, which were just colors, I'll just push them out here. So out vec3 call, so that they get interpolated. Oops. So that they get interpolated properly in the fragment shader. I'll pull it in, and then I'll just say it's the texture, and we'll add the color to it. So plus call should be enough. And call is vec3. Actually, it'll have to be a vec4 call, and then 1.f or 1.0. And so you can see the only thing I've changed is my VertexBuffer and my shader to match. And now if I run this, the hope is that I have some different colors per vertex all being nicely blended together. And you can see that that is the case. There's my white, my magenta, my blue, and my green. So there, that is exactly what we wanted to get to, where we're in a place now where we can easily add data per vertex, easily modify exactly how we want to lay out that data so that it works with the specific layout for a shader, and do it all without having to change the engine, right? That's the key. I don't need a new mesh constructor. I don't need a new version of Hippo. I just need to define my data here in line with this brand new API that we've created. So hopefully you found this interesting. I know the only real change we've seen here is that we're now having colors on our texture, but I think really the interesting change here is that the backend support for this dynamic arbitrary upload, and then how we expose that to an API to the user. So that's it for today. If you made it this far, thanks a lot for watching. Please remember to click that subscribe button, give me a big thumbs up, and I'll see you in the next video. Cheers.